This is my joint work with Jianbo and Jia, titled A Distance for HMMs based on Aggregated Wasserstein and State Registration. A hidden Markov model is a generative stochastic model for sequence data, and it has wide applications, for example, in speech recognition, human motion classification, and gesture recognition. In these applications, we commonly use Gaussian mixtures as an emission function, so there is a marginal JMM associated with each HMM. Thus, a HMM can be specified by a number of states, here 3, a transition matrix, and mu's and sigmas for the Gaussians. Here, we visualize a 3-state hidden Markov model, and we use squares to represent the atoms in the transition matrix. A distance for HMMs is critical for HMM-based sequence retrieval, sequence classification, and sequence clustering. In the literature, the most widely used distance between HMMs is a KL divergence-based distance. The distance is likelihood-based and uses forward-backward algorithm. So, it relies on the original sequence data at hand or need to generate long sequence from one of the two HMMs for computation. In this work, we take a different approach and propose to minimize the aggregated Wasserstein and improve the aggregated Wasserstein. Our approach solely relies on the parameters of the two HMMs in comparison, and there is no need to generate long sequences. Also, we find MAW and IAW shows better differentiation ability in experiments. First, minimize the aggregated Wasserstein. The computation of MAW takes 3 steps. First, we want to align the states of the two HMMs so we know which state corresponds to which. This is called state registration. Here, we visualize a 4-state HMM aligning to a 3-state HMM. From intuition that states have higher correspondence should be geometrically close, we use optimal transport to solve the registration matrix W, which is an optimization problem. Once the blue registration matrix is solved, we can easily transform one HMM's transition matrix to the others. For example, here, we transform HMM2's 4x4 transition matrix to HMM1, resulting in a yellow 3x3 transition matrix. In symmetry, we can also align the 3-state HMM to 4-state HMM. For the limit of space, we don't show it here. State registration is very important in our framework and paves the way for both Step 2 and Step 3. In Step 2, we measure the difference between the marginal JMMs of the two HMMs in comparison. The difference is specified by a weighted sum of the Wasserstein distance between every pair of the Gaussian component, and that's why we give the name Aggregated Wasserstein. In Step 3, we measure the difference between two transition matrices of the two HMMs in comparison. After the alignment of the transition matrix such that the dimensions are the same, we compute the difference by summing up the corresponding rows' marginal JMMs difference using aggregated Wasserstein. And finally, the distance is defined by a weighted sum between the difference between Gaussian mixture model and the distance between the transition matrix. Improved aggregated Wasserstein is an improvement over MAW, in that we compute a more accurate registration matrix, and the following steps are the same with MAW. We sample n points from each of the two marginal JMMs, and then get the registration matrix by computing the optimal transport plan of the two endpoints. With more accurate registration matrix, we expect XAW to have better differentiability, but at the cost of lower speed. We do both synthetic data experiment and the real data experiment to validate MAW and IAW, and find that MAW and IAW has better differentiation ability than KL-based distance. In the synthetic data experiments, we aim to compare MAW, IAW, and KL in terms of their sensitivity to the perturbation of the 3 HMM parameters. We observe MAW and IAW performs better than KL under the perturbation of mu and the perturbation of transition matrix, and the IAW performs on par with KL under the perturbation of sigmas. For real data experiment, we use CMU human motion time series data for retrieval and classification. We again find MAW and IAW performs better than KL in terms of area under the curve for retrieval and classification accuracy. Thank you. For more details, please refer to our paper and welcome to our poster spot.